One of the ways that cells and membranes in the natural world maintain strength is with something called pre-stressing, where the membrane is put into tension before. So let's think about pre-stressed concrete, where we put in stress before we load up the rest of the building. What we need to remember is that concrete is weak in tension. It cracks like crazy. And as you probably remember, when we have a beam and we put a load on it and the beam bends, the beam always bends, and that means the bottom of the beam stretches. It's in tension. And what happens to the concrete down there? It cracks because it's getting pulled apart. Concrete is weak in tension. So this is why we put rebar in our beams, but even the rebar cannot always prevent the cracking when we have a big beam and a heavy load. So manufacturers have two ways of reinforcing the strength in a concrete beam. One is called pre-stressing and one is called post-tensioning. And you can recognize those two words or those two prefixes. Pre means before, so pre-stressed is tensioned before, and post means after, so post-tensioned is stressed after. And let's see what that is. In post-tensioned, which is this top image here, cables are put into the beam and they are tightened after the concrete cures. And they go through these conduits so the cable does not actually touch the concrete. In pre-stressed beams, which you see in the bottom picture, the cable is tightened, then concrete is poured in, so it's tightened before the thing is put into place. And because the concrete is poured around the cables, the concrete actually bonds with the cable. In pre-stressed concrete, they put cables inside the formwork. These are high-strength cables. They use turnbuckles or something else to tighten the cables. They pour the concrete. Then they cut the cable, and because the cable is in tension, the beam gets a camber. It gets a positive camber like you see in this picture of a sponge at the bottom of the slide. So that the steel is in tension, the concrete at the bottom of the beam is actually in compression. So you wind up with a concrete beam with a positive camber in it and the bottom of the beam in compression, which is what you prefer because concrete is great in compression. This pre-stressing, where you put the cables into the formwork and then you pour the concrete, is done at the factory, so it's done off-site. A local example, if you're in the Eugene-Springfield area, is at Knife River, which makes concrete beams and other structural concrete for highway bridges and that kind of thing. So here's an example, and you can see that positive camber that's been put in after they cut these pre-stressed cables. So they work it out so that the compressive stress at the bottom of the concrete beam exactly offsets the tensile stresses that would have happened in a plain old reinforced concrete beam when you put a load on it. It's pretty cool. So it has a lot of advantages. The disadvantages are obviously high strength steel cables are probably expensive. And then it requires people with expertise who can inspect the work closely and good quality control, which a company like Knife River has, obviously. Me doing this in my backyard would be a very bad idea. Knife River, they know what they're doing. Now let's think about post-tensioning. In post-tensioning, these tubes, these conduits, are put into the formwork, then the concrete is poured over the tubes. Then afterwards, after the concrete cures, these cables are run through the conduits and they're tightened, and that compresses the concrete. And those conduits actually drape. I'll show you some pictures of the LCC Downtown Center in a minute. It has the same effect as the pre-stressed examples we looked at, which is that after the cables are tightened, you get a positive camber in the beam, you get an upward curve, and that puts the bottom of the beam in compression, which is what you want with concrete. Because remember, concrete is terrible in tension, but it's great in compression. This post-tensioning is done on the job site, and they use these special tools that grab hold of the cables and pull on them and tighten them. This is a close-up of a concrete beam in a highway bridge. So the cable goes through this concrete, and it does not touch the concrete. It just is loose in the conduit stuff. This is a photo of the construction of the first Beltline road flyover over Interstate 5 highway. This is near Eugene and Springfield. And this flyover, this overpass, used post-tensioning. Here's a picture of a worker cutting the cables after they've been tensioned. So this overpass, the longest ones were 275 feet long with 16 tubes in them and these great big cables. And when I don't have a picture of their hydraulic tool that pulled on the cables, but the report in the newspaper was that 1 million pounds of force, 1 million pounds of tension was used to pull on those cables. That is a lot of force. And so they pull on those cables, they attach the cables so they are now in tension, and then the worker uses a saw, a cutoff saw, and cuts the cables, and those long beams, those 275-foot beams, cambered so much that they got 6 inches shorter. One of the workers who was doing this contracting work reported that after you put 1 million pounds of tension on those cables and then you cut it with a saw, the sound is like an explosion. The worker said it was really frightening the first time they cut it because it makes a huge noise. This is just a page out of the AASHTO standards where they're showing standards for various kinds of bridge beams and where to put stuff. I just thought that was interesting. This is a picture of the Jaques Center at the University of Oregon. This is that big glass cube where athletes get help with academics, and this was when they were just finishing it. Here it was under construction, and so they have concrete beams with lots of post-tension tubes under them, and here are the cables poking out of those tubes while they're waiting for the concrete to cure. The LCC downtown campus has a lot of post-tension concrete in it. So here it is under construction. There's the academic portion. And that building was constructed by a commercial contractor named Lease Crutcher Lewis. They're very generous in working with LCC, so they shared some of their drawings and photos. Here is a floor plan of part of that building. And notice these grid bubbles. If you've studied structural steel or commercial building plans, you're familiar with the idea that every commercial set of plans uses these grids, it's like in a map. So there will be letter names spaced every so often. Here is D, E, F, G. And then there will be numbers every so often, 1, 2, 3. And so you can locate any column in the building with its grid location. So here is column F2, and it's F2 all the way from the basement to the top floor. Here's a Lease Crutcher Lewis drawing showing how that conduit is actually draped through that beam. And this drawing would have been drawn by a drafter at their company. Typical detail. Here is a plan showing where those cables will run through. And again, here are the grid markers. And another plan showing some anchor attachments. Here are some details of attaching those tendons. And then some photos showing them draping those conduits through the formwork. So here you see the rebar, the reinforcing bar that lies at the bottom of the concrete. Over that, here is the draping of the conduit. Here's some more. They've gotten some more conduit put in place. And here's some more conduit, and notice they are labeling this photograph. This is at grid location B6, so we know right where we are. And then here they are. They have gotten all of the rebar and all of the conduits in place. Now they're beginning the pour. They're pouring the concrete over these. There's the hose from the concrete supplier. And they'll let this concrete cure, and then after some days they'll come back with those hydraulic grabbers and tighten up the cables.